welcome. My name is Douglas Santos. I'm a security strategist for FortiGuard Labs, which is Fortinet's threat research and response group. My background is mainly in network security consulting and architecture, but for the past year, I have been dragged, if you guys will, into a threat research group where my main responsibility is first understanding how our detection technology works, understanding which are the threats that are coming and targeting our customers, and giving guidance as to which kind of which version of IPS engine or AV database engine they should be running in order to be able to mitigate a certain threat. Another key responsibility of mine falls within being kind of a proxy, if you will, between all the development that's being done in our labs, the IPS engine development, AV engine development, new technologies, new products, understanding how this works and formatting it and communicating this to our customers, partners, and sales organization, so they can have a better understanding of what technology we're working with, where we're going with that technology, okay? And one of the products of my work is this presentation that I've drafted by talking with some of the guys responsible for putting together the machine learning systems that we have of Fortinet that helps us tackle the huge problem, which is this increasing sophistication and volume in virus that we have seen over the years. So just take us 1,000 steps back and understand what was the first level of antivirus evolution. Does anybody know? Have any ideas? How would the first antivirus engine worked? Hashes, right? So simple MD5 or SHA-256 computations would generate a uniquely identifier cryptographic identification of a malware. And then this obviously has implications, right? If you have trillions of virus samples, as we have today, Fortinet has 0.5 petabyte in virus samples. That accounts to dozens of trillions of samples. If you have a hash for each one of those files, this is obviously not a very smart approach, right? You end up with a huge database, the performance implications will be huge. This obviously won't work. So that means one signature, one piece of malware. It is reactive by nature and non-responsive to mutations. So if you get a virus sample and you run a cryptographic algorithm on that, you have the hash signature. If you open up that virus sample in a disassembler and change just an op, the signature will be different. Your whole protection will be gone, right? So this antivirus relied on cryptographic libraries such as MD5-SUM and SHA-256. And what the program will do, they will simply scan through all the files in the file system and would run the cryptographic routines on those files, having those files as input, and then would compare the hash signature with a known database of malicious samples, right? That's obviously not too smart. So here comes level 2. Fortinet has developed, and I think that other antivirus vendors have similar engines that are able to strip down and understand patterns of behavior, okay? And it does that by something that is called content pattern recognition language. This was a patent that was granted to Fortinet in 2012, and that basically allows products such as the FortiGate to open up zip files, password-protected files, packers, mostly commercial packers, and try to understand what this malware is doing at the memory level, when it's starting to decode instructions, when it's starting to do memory operations. And this is at the gateway level, okay? So it allows us to write one signature and catch any times of permutations on the signature. So what we usually do is that we usually write a CPRL signature for a specific malware family. Okay, so pieces of code that are used amongst those various families, we try to write signature that will get on those behaviors. Okay, it's proactive in nature, and it's basically able to look deeper into the code. So if you have, for instance, a zipped malware or a password protected or even packed malware, most of the information that would you would need to identify that piece of software as malware is encrypted or it's hidden right from plain sight. So as a network level antivirus, you must be able to strip all this information from packets, reassemble those packets in memory, and then call the CPRL routine to make sense of if that information that's present on memory matches a given signature or not. Okay? So what does a custom packet sample look like? Well, all of the information that is available so that you can understand if this is a malware or not is encrypted, okay? Everything that you have that is visible code is just a decryption routine, okay? And then all the data is obviously encrypted. So what's in this decryption routine? Basically, instructions to allocate memory, decrypt this data, inputting this data into the allocated memory location, and then jump to the decrypted code. So what it does is just basically allocates a memory block, and then it's starting to decrypt the data, okay? And once this is happening, then once this is actually finished, then our content pattern recognition algorithm will be able to take a look into the memory location and understand if that that information matches any kind of malware signature that we've seen in the wild. Malware code reuse is a big thing. If you write a signature today that has a certain function, more likely than not, you'll be able to catch other malware with the same signature that's reusing that same function, okay? So, yeah. So, but writing a CPRL signature is not an easy task, right? As you can see here, this is a simple, kind of a, not very simple, because you can see here we have some functions. Here we have information about byte comparison. If you find some kind of byte pattern, you can then jump to a certain location and look for another byte pattern. If that's found, then you can write simple features, functions to go deep into the code, trying to find, for instance, the decryption routine or the decryption key. We can do all this at the network level, okay? But of course, writing a signature is no easy task. It requires a reverse engineer, a person that has extensive knowledge of our content pattern recognition algorithm, and they must understand which parts of the code would help more in detection, right? Which are the parts that should be reused, right? And we do this by replicating, by getting information by getting various samples that are somewhat similar, and trying to see if those features that I'm using to identify this malware can be used to identify other malware that's similar, right? And then we have detection, right? We gotta check this signature to see if it will be able to detect the malware that we wrote it to get, and it's not gonna be triggering any false positives on clean samples as well. That's very important, right? That basically allows us to take a glimpse into the future and understand that if any piece of malware has any information that is present on this signature, then it will probably be detected, right? It doesn't matter if it's packed on another packer. It doesn't mean anything if it's on a RAR password protected file. This thing can rip it apart, okay? So the current issue is just volume, right? On a given day, Fortinet ingests from 500,000 to 1 million virus samples, averaging 700,000 virus samples a day. That's a lot, right? So to cope with this problem, we first created CPRL, which is a signature that allows us to catch a whole bunch of viruses from one given family with one signature, so that we yielded a smaller database, so we can provide that to our customers, right? It does this because it is able to emulate 32,000 Windows API syscalls. So as the malware is traveling to the FortiGate is able to look at the packets, reconstruct the packets, and once the packet is reconstructed in memory, do a virus check, okay? Even if it's zipped there or packet protected. But even so, that was not enough. So we created what is called the auto CPRL. It create signatures automatically, trying for two things, 100% detection and 0% false positive. Okay, it creates close to 500 to 2,000 signatures a day, but this still resulted in large levels of manual effort. Okay, and that's because we weren't checking extensively for performance, but we have built a system that uses reinforcement learning that takes that into consideration. So I'm gonna go. I'm gonna talk to you guys about this. Okay, so. What mighty technology might help us? Anyone can think of anything that can help us tackle the sophistication and the ever-changing nature of malware? Machine learning, right? So we have close to a century of the first person that was able to understand that we were able to make a machine learn something, and that was Alan Turing, right? Turing, Klein, and Church, they proposed a machine learning solution in the 1930s, and they were basically trying to understand if any problem that could be categorized as a rule of thumb could be made possible to make a computer learn that this was this and different than that. So for instance, we know that a car, if you look at a picture of a car from the side, you have two round objects, you have kind of a rectangular object, there are mathematical proportions between them. So they're just trying to, okay, if I can measure this and I have a database of what this looks like in measure, I could certainly make a machine understand that a car can have these proportions, right? And in 1943, McCulloch and Pitts created the formal design of Turing's artificial neurons. When they are doing this work, they started playing around with the concept of inhibitory or excitatory signals and backtracing. Okay, so they're trying to evolve the field, right? Into 1956, when the first AI course was founded at Dartmouth College, it didn't take long for the U.S. military to take a great interest on this, right? And in the 1960s, there was a very popular experiment from the army, from the military. They basically were trying to see if a computer was going to be able to differentiate a tank, a picture of a tank from a picture of a tree. Okay, so what did they do? They got a hold of all the tank photos, the photos that they could, all the tree photos that they could. They feed it into the model, and they say, hey, it works. Oh, nice. Let's open to the world. What happened? Their model failed. Why? Because they understand that most of the pictures that were taken from a tank were taken on a cloudy day, and the pictures from the tree were taken on a sunny day. So the mods, in order for a model to have success and be able to predict with a certain amount of certainty, you have to have a huge amount of data. Right, you gotta consider everything basically. So that's basically the failure to comply with expectations led to the first AI winter, where research money was taken away from these institutions. Up until 1980s, when the x86 and Lisp started to sprung, giving more computing power, and up until the 1990s. When AI applied to data mining and medical diagnosis, surpassed by a great amount the accuracy of a human analyst trying to find signs of any disease on images. And that's understandable, right? We can't see pixels. So a machine will be obviously way more able to do this. So in 1997, IBM Deep Blue beats Grandmaster Kasparov in chess. We're starting to chart into deep learning territory, and into 2011, when IBM Watson defeated the Jeopardy Jeopardy champions Brad Rutter and Ken Jennings. There was a very strange phrase, not strange actually, but from Ken Jennings, he said that I for one, after he was defeated by the Watson, he said, I for one welcome our robots overlords, right? So we're just trying to make a little bit of a joke, right? I guess. So yeah, 2013, Watson application for management decisions of cancer lung treatment, depending on lots of information from the the patient and the aggressiveness of the tumor and the drugs that were available at the time. It was able to propose very specific treatments, right? And enter 2015 when there's more than 2,700 AI projects at Google. One of the most interesting that I think is one by YouTube, where you know when a YouTube user uploads a video, it can tag, oh, okay, I just made a video of my cat playing on the snow. Cat playing snow, okay. But there could be more to that video, right? So YouTube is now writing, 2015, sorry. Wrote a program so they could take pictures of the videos and try to identify other things on the images so they could auto-tag. So just one application so you guys can understand. And 2017, Elon Musk calls for the regulation of AI and actually social media as well. Anything that could have a disturbing impact on society that should be regulated. I agree with him. So let's delve a little bit into machine learning, okay? Anyone ever heard of supervised learning at all? Have any idea what it is? Good, good. Supervised means that somebody is looking at it. Somebody is feeding the system data and telling the system which kind of data that is, okay? So an input file is identified as either malicious or clean in the case of antivirus. So we have a model, we build a model, we get a bunch of samples and identify them. Hey, these samples are malicious, these samples are clean. Understand what makes them malicious, understand what makes them clean, okay? System needs to be trained. This is exactly what I'm talking about, and then tested, okay? So the model initially extracts feature set from an initial file, so it's basically looking at, if, for instance, the virus is a PE file, it's looking at the file structure, the DLL file imports, functions, entropy of sections, it's looking at the code blocks, right? Then weighting values are applied. The weighting can change based on the frequency of certain features on the malware set that's being analyzed. If you're seeing that this feature is present on 100% of the malware, then it's a malware. It's a malware feature, right? So expert humans make tone and guide feature sets, and this is extremely good for malware detection. Okay, it allows you to clearly identify certain patterns from one side, which are not on the other side, on the other samples, right? And then we have unsupervised learning. So machine learning is very good for malware detection. Is this a malware or is it a clean sample, okay? Then we have unsupervised learning that uses no tags and does not need supervision, right? Data is initially unlabeled, so it presents an unknown state to the AI. What the AI will try to do is to try to find commonalities between those data and aggregate those data based on those commonalities. So what would this be good for? Anyone know? Grouping of malware into families, right? So the results produced through inference, the output's not actually evaluated for accuracy. Yeah. Unsupervised methods include clustering, which is basically trying to group malware families into families, and anomaly detection, right? Learn normal behavior and then try to find any deviation of patterns. That can be applied to network traffic detection, any anomalies that you may find. So that helps you group different populations into different families. And then you have reinforcement learning, okay, which is based on an action reward, okay? It consists on an interpreter, an agent, and the environment. The result is produced through observations and modifications of the state of the agent. These modifications have an impact on the environment, and the reading of the environment will define if the actions were good towards the end goal or bad, worse than the last observed state. So why do we use this? For signature creation, okay? We have supervised learning looking for features in those little tiny tidbits of information that makes malware malicious. And we have information about the syntax of the CPRL language when we have the data sets, right? So it's basically trying to look for those features, see how we can write a signature, test for the signature for three things: 100% detection, good performance, and zero false positive. I'll get into it after some slides as well. I'll go deep into this. So a little bit about models, features, and classification networks. Okay, One type of artificial neural network, we have a couple of them, support vector machines, random forests. This one I'm going to be talking to you guys is called the multi-layer perceptron, and this is what we are using right now to do feature extraction and malware classification. So it consists of 3 or more layers. We have an input layer, 1 or more hidden layers, and then the output layer. Okay, layers are made up of nodes, okay, connected to every node in the previous and subsequent layer. Okay, each node is going to be responsible for either finding or extracting a given feature. Okay, so and each feature will also have a weight. Okay, so as the system is training and it's seeing that feature X, Y, and Z is happening to be found in 80% of the malware, then it's going to have a higher weight than a feature that's only found in 10% of the malware, for instance. So the multi-layer perceptron is similar to human neurons. If its input is strong enough, the signal is passed according to a weighted value. Okay. Layers, nodes, and features allow the systems to learn. Okay, so the system is fed initial data sets for analysis. In the case of the supervised machine learning, you gotta say, hey, model, this is a malware file, and this is a clean file, okay? Which is basically the supervised machine learning approach. When the system, when the file enters the system, then the feature extraction part of the model takes place. And this is a part that requires a lot of domain knowledge. So you gotta know exactly what to look for and where to look for, so you can identify that thing is malicious or not. So what we call the features are extracted during this learning phase. What are those actually features, right? Basically, file header structure and fields, in the case of static analysis, assembly engrams present within the blocks. If you guys ever saw a executable file in a disassembler, it has these little blocks. At the end, there's a conditional statement that may branch to yes or no, and then you have another block of assembly instructions. Okay, this obviously needs to be normalized, because if you get two viruses that you are probably using the same function, something may be different. Like they may be using another register, or the memory locations are different, or the functional names are different. So anything that could change between those malware needs to be normalized, so we can do feature representation and not end up with a huge search space, right? So the system learns by weighting features based on surety of indication and frequency of observation. Okay. So those features are just point observable characteristics based on code blocks, right? Parsed when they enter the system, they have one-to-one relationship with nodes. One node is going to be responsible for looking for that specific feature or extracting it. It depends on the state of the system, right? We have a rolling system where we have a system that's actually running, that has been trained, and we have a system that is constantly training. After 3 weeks, we switch them. Okay, so we have the last feature set of the newest malware to be run against with the new malware that's coming in. So we have a rolling system, so it's always updated, right? They are maintained in a knowledge-based repository. Features, CPRL, signatures, and other information. Obviously, there's a motto in machine learning: the quality is critical. Garbage in, garbage out. So you gotta be sure that you're feeding the system the very best representation of malware and the very best representation of clean files, right? So we are leveraging our internal legacy samples, which, as I told you guys, close to 0.5 petabyte of virus samples. Yeah, and obviously, as I told you, the feature is weighted to assistant decisions. It's basically on surety of indications and the frequency of observation of that feature amongst a population of virus files. Obviously, the feature weighting can change over time. So let's see that we have seen a sample today that is using, there's a good one. The Cuckoo sandbox was using layer 3 hooks in order to look for malware and to trace the execution flow of the program. But we, at Fortinet, we have seen a malware that was able to bypass the Cuckoo sandbox layer 3 hooks. It's simply a function, right? So at the time of the virus, that was a feature that was probably very important. It was being seen on malware every day. So it's a heavily weighted feature. Okay, so then researchers got a hold of the sample, reverse engineer it, looked at how it was doing the level 3 hook, patched Cuckoo Sandbox. That thing won't show anymore. So the feature weighting will slowly decrease, and will be kicked out as new features are coming in and the system is assigning random weights to it. So it's how the system evolves and maintains a good feature set of what's more important to detecting malware, right? So yeah, just so a little more information here. As I told you guys, we have the input layer that's basically doing file typing. We have different types of malicious artifacts, Word documents, PDF documents, ELF files, PE files, DLLs. And then once the file typing is done, it's going to be looking for some features on the malicious layer. Okay, so let's say it finds a feature that has a weight of 90, and it finds a clean feature as well on the malicious file, because malicious software does not always have only malicious features. Then let's say it's 70, okay? So the result is like, okay, so if more than 50% of the population of the malware is like have 70% of maliciousness, then it's probably malicious, right? So, and that's obviously on multiple instances, right? We have millions of nodes looking for specific features, so the result is the calculation of millions of malicious features and millions of clean features, okay? So we have two classification networks right now. We have a fast classification network that's more interested in looking for static information on the file. So it's not executing, it's not doing anything, it's just looking at the PE file structure, the disassembled version, and that's it. So PE file structure. And we have a slow classification network that's basically looking at other things such as register information, memory, results, call stack status, exit status. So we're using machine learning for both static and dynamic analysis of the code. And then those are both features that are going to be built into a feature database. And then we have the reinforcement learning module that's going to try to look for those features, write signatures, and see which one of these features is better at detecting malware. Okay, so it depends on case to case. So the classification networks generate a unique static content identifier of an abnormal file content. We have three layers. The fast classification layer, we does raw file analysis, which, as I told you guys, looking for this type of information, such as PE file structure, PE DLL imports, assembly n-grams, code blocks, and functions. And we have the slow classification network, which does dynamic file analysis. We're not actually doing sandboxing per se. We are actually leveraging our CPRL and our ASICs to be able to do this very fast. Okay, so we do a CPRL emulation of the assembly n-grams, that basically gives us information such as instruction results, call stack status, and execution flow. So the order of the assembly n-grams. Because one thing that could defeat this model, and that was addressed at a talk at Black Hat last year, was from a guy from Endgame. He basically built a reinforcement learning module to try to fight and create malicious executables with a lot of clean features so that it could bypass the model. So he had to have the model, and he had to be able to look at the results of the model and try to modify his malware on the fly so he can try to beat the model, right? So when you look at the execution flow and the topology graph of the malware, if those clean features are not hit, so that's they have no use, right? They have no use, right? So, and then we have the identifier generation network, which uses the reinforcement learning and does generate the auto signature. So it generates a unique identifier of abnormal file content and uses output from both layers to selectively design the best features. It's looking for signatures that will yield 100% accuracy, 0% false positive, and good performance. Okay, if it finds that balance, then the signature is automatically deployed. Okay, so in order to build a signature, we don't actually need to match all the features of the malware, right? We gotta make sure that we understand what are the commonalities between those malware in the malware families and leverage that in order to write a signature. So let's say we have 5 features that's gonna be used to write a signature to detect those malware that generate us let's say 1,000,000 features, okay? Now let's take 5. Write a signature, try to detect this malware, try to see if any other clean file is not falsely detected by this guy. And then he understands that he has 100% detection, 0% false positive, but the performance is very poor. So what it does is selectively discards one feature, brings in another one, does the same thing. If the performance is a little better, then the system has learned that the feature that he had kicked out is bad at performance. Okay, so this is how the system evolves and uses all this information. So it leverages information from both classification networks and group mappings for the unsupervised learning, so it can learn which kind of malware should be tested against a given signature. So a little bit of graphics, so you guys can live with a very clear understanding of this. So as I told you guys, on system training, we are using the supervised machine learning perceptron. So we start the AI model with an empty feature repository, right? Then we got a hold of a bunch of virus samples, malicious samples, and clean samples. We labeled them, and we feed them into the model. And then the model will get information from malicious sample, we'll send into the malicious layer for feature extraction, we'll get a hold of the clean samples, we'll send the clean samples to the clean layer for feature extraction, and then at the end of the system training, we end up with a full feature repository that's the representation of both the malicious and the clean features, right? The features can be modified when system learns. So we have a feature repository, and we are inputting, trying to train other malware. So it's looking at the feature sets from this malware, trying to understand if those features are already present, if they're not, if they should be inputted and considered for the next rolling system, right? So once you have tested, trained the system, it's time to test. On system testing, we don't label the samples. All we do is just feed them the samples. Okay, so now the work of the model is try to look at those samples and identify within those samples the features that it had identified before. And these are other samples. Okay, you're not using the same samples. You're using other, because remember, we want to make sure that we're using features that are reused amongst malware authors. Okay. So using the feature repository, the samples are analyzed. As this occurs, features may get modified or others added, as I told you. So the system determines the clean or malicious output of another given set of files. Okay, and then we are able to look at the results and see, oh, okay, this had yielded 99.90% accuracy. Oh, that's good enough. Oh, it has yielded 97, 96. Not good enough. Let's get a hold of another sample. Let's try to train this and see if with this other set of files we'll be able to achieve greater detection, because those samples will have features that's more used or reused by the malware authors. So our AVAI in operations, basically, as you guys can see, the files are sent to the system. The malicious will be stopped at the malicious layer. They will do feature extraction or feature testing, depending on the state of the system. And then system will start sorting out malicious and clean samples based on presence of features that it was able to found on the samples, right? And as the system is running, we have a lot of feature set improvements. We have increased quality, a stabilized number, and a weighting confidence that a given feature is really malicious and that a given feature is really clean. Okay. So what happens when we gotta train the system with new malware, right? We have close to a little bit over 120 threat feeds and plus 3 million global sensors. These sensors send us information about these new malware samples, right? So as this malware is entering the system, the feature extraction is breaking those malware into understandable code blocks, and those code blocks are then fed into the slow classification and fast classification network for no matching feature sets. Okay, When there's a new malware management system, new malware enters the system. The system tries to understand which kind of features are new, which are not present on the system. So let's say that the malware that we're training have 1,000 features, and 30% of those features are new features. We start up a mini repository with only those features. We get a hold of another set of samples and try to identify if those new features are good at identifying samples. Because we're gonna make sure that if you're gonna use it, they're gonna be useful, right? So if they are sent to a repository and then into the production feature set. So how does all of this ties together, right? We have our new selected virus DB, which is fed to the supervised feature extraction, which feeds a feature repository. And then we have an unsupervised malware classifier that's basically trying to group those features and those malwares together so that the reinforcement signature can then look at those features, look at the group mappings, try to create signatures and test them for good performance, 0 false positive, and 100% detection. Okay. Well, that was it.